Right now, you're standing on a planet hurtling through space at nearly 670,000 miles per hour. This planet Earth orbits a massive thermonuclear star, our Sun, which outweighs it by more than 1,000,000 times. Yet even this star is just one of over 400 billion others shining within our galaxy, the Milky Way, a cosmic system so vast that light itself takes 100,000 years to cross from one side to the other. And here's the truly staggering part. Our entire galaxy, with all its countless stars, planets, and possible civilizations, is just one tiny speck among 2 trillion other galaxies scattered throughout the observable universe. If you appreciate explorations that transform your perception of existence, press that subscribe button and follow along. Prepare yourselves. Our journey starts now. Envision yourself positioned in central Manhattan during the midnight hours. Illumination spreads infinitely across all visible directions. Structures disappear into shadow at the distant edge. Now conceive of this urban landscape expanding not merely to neighboring states, but spanning the entire continental United States territory. Then extend it beyond the Pacific Ocean, reaching Asian shores. Continue stretching it completely around Earth's circumference. Then increase that measurement by 6 billion times. You've now mentally mapped our galaxy's breadth. Through rigorous measurements, scientists have validated that the Milky Way extends 100,000 light-years between its furthest points. A single light-year corresponds to 6 trillion miles in distance. This indicates our galactic residence measures 600,000 trillion miles in diameter. Recording that figure completely would demand a sequence of zeros extending from your residence to your closest market. Yet here emerges the initial assault on human comprehension. Despite this consciousness-crushing magnitude, our galaxy constitutes merely the initial rung on a cosmic staircase ascending toward infinities our cognitive abilities cannot grasp. Every individual luminous point you observe sparkling in the nocturnal heavens belongs to our galactic vicinity. The hazy stellar band cutting through darkened skies exposes the profile perspective of our spiral configuration. We inhabit this cosmic metropolis embedded within its architecture like an individual cell inside a colossal organism. From our location approximately 26,000 light-years from the galactic nucleus, we can witness stellar creation zones where nascent suns ignite. Annually, we observe stellar birthing grounds where gravitational forces sculpt gaseous clouds into blazing spheres. Aged red giant stars conclude their existence in dramatic detonations that distribute heavy elements throughout space. This entire cosmic performance plays out within our immediate galactic environment. Yet what renders this magnitude genuinely unsettling isn't its dimensions, but rather what it signifies. Our galaxy constitutes merely one component in a hierarchical system of structures that becomes progressively vast and beyond comprehension. Each tier of cosmic arrangement dwarfs its predecessor by magnitudes that make human existence irrelevant. Occupying Earth and pondering galactic separations resembles an insect attempting to understand North America's extent. The insect can perceive that something enormous exists beyond its immediate surroundings, yet lacks the mental framework to comprehend continental dimensions. Humanity confronts identical limitations when facing cosmic separations. Our developed brains, engineered for hunting across African savannas, struggle with magnitudes beyond our immediate surroundings. This mental obstacle becomes our initial indication that the universe functions at tiers far exceeding human intuition. Each cosmic formation we uncover compels us to relinquish our terrestrial viewpoints and accept magnitudes that seem more like mathematical concepts than physical existence. Ancient Greek civilization believed the celestial bodies were perforations in a heavenly dome encircling Earth. Contemporary astronomy discloses that our galactic residence alone harbors enigmas that would have surpassed their most extravagant speculations. Every telescope probing deeper into the cosmos uncovers additional tiers of cosmic arrangement extending toward boundaries we can scarcely perceive. Yet, in comparison to subsequent revelations, our galaxy resembles an individual chamber in a cosmic estate with innumerable levels extending toward infinity. Photons travel more rapidly than any other phenomenon in existence. Nothing can surpass a photon racing through spatial vacuum. At 670 million miles hourly, illumination circles Earth 7 times within 1 second. This cosmic velocity threshold represents the maximum possible speed for traversing separations in our reality. Yet even illumination, the supreme velocity champion of physics, demands 100,000 years to journey from our galaxy's one extremity to its opposite end. Consider the implications for human understanding. The illumination departing distant stellar bodies in our galaxy this evening commenced its voyage when primitive humans initially learned to create flames. Photons currently arriving at Earth from the Milky Way's distant side started traveling before written communication existed. These primordial light particles convey information regarding stellar occurrences that happened when our forebears were still discovering agricultural practices. Scientists employ this light journey duration as a cosmic measurement tool. When astronomers examine distant galactic territories, they perceive them as they existed millennia previously. The galaxy we witness tonight actually represents a patchwork of distinct temporal periods. Proximate stars display recent occurrences. Distant stellar communities expose ancient chronicles. We never observe our galaxy as it exists presently, but instead as a time-averaged compilation spanning thousands of years. This temporal displacement generates one of astronomy's most peculiar validated realities. Every photograph of our galaxy displays multiple temporal periods concurrently. The illumination from various galactic territories departed their origins at different historical instances. Observing the Milky Way means observing backward through time across a duration exceeding human civilization's existence. Yet this journey duration becomes even more consciousness-altering when we contemplate galactic rotation. Our complete galaxy rotates like a cosmic pinwheel. The solar system circles the galactic nucleus once every 200 million years. Throughout light's journey across our galaxy, the complete structure accomplishes nearly half a rotation. The galaxy literally transforms its configuration while illumination travels between its territories. Even more disturbing is what this suggests regarding cosmic interaction. Any endeavor to transmit signals across our galaxy confronts this fundamental obstacle. Radio transmissions and laser projections travel at light velocity, meaning galactic interaction demands patience measured in geological epochs. If an extraterrestrial civilization on our galaxy's opposite side transmitted us a communication today, our remote descendants' would need to anticipate our remote descendants' receiving it. This interaction obstacle means that our galaxy can never operate as a unified entity. Distinct territories function autonomously, separated by the fundamental velocity limitation of information transmission. What seems to be a singular cosmic formation actually comprises innumerable autonomous zones, each developing without awareness of distant galactic communities. The primordial photons arriving at us tonight convey communications from a galactic history we can witness but never revisit. Every stellar body we observe informs us about circumstances that existed before our species learned to gaze upward at the nocturnal heavens. And yet, This galactic interaction challenge represents merely the most minimal scale problem we confront when attempting to grasp cosmic separations. Venture outside on a cloudless evening and identify the most luminous stellar object in the firmament. That brilliant luminous point is Sirius, burning 25 times more brilliantly than our solar body. It shines so luminously that ancient societies based their calendars upon its movements. To your perception, Sirius appears proximate enough to reach with a sufficiently elevated ladder. The validated reality destroys this misconception entirely. Sirius lies 8.6 light-years distant from Earth. This separation equals 51 trillion miles. If you could operate a vehicle at highway velocities toward this nearest brilliant star, the expedition would require 300 million years. You would need to sustain 65 miles per hour continuously since before complex organisms evolved on Earth. Yet Sirius is practically adjacent compared to characteristic galactic separations. Most stellar bodies in our galaxy are separated by intervals so immense they defy human comprehension. The typical separation between adjacent stars measures 4 light-years. In cosmic terms, this represents an almost flawless vacuum interrupted by occasional minuscule islands of substance. To visualize this emptiness, conceive shrinking our solar system until the sun becomes a basketball's dimensions. At this proportion, Earth would be a sand particle orbiting 26 feet distant. The nearest stellar body would be another basketball situated in a distinct municipality, perhaps Denver, if you initiated in New York. Everything between these basketballs contains essentially nothing except vacant space. This emptiness generates profound ramifications for space exploration between stellar bodies. Even traveling at illumination's velocity, expeditions to proximate stars demand years. Conventional spacecraft moving at achievable velocities would require tens of thousands of years to arrive at the closest stellar companions. The overwhelming majority of our galaxy remains perpetually inaccessible to human investigation. The emptiness between stellar bodies also clarifies why extraterrestrial contact appears so improbable despite the tremendous quantity of potential worlds. If extraterrestrial civilizations exist on planets circling distant stars, they confront the identical fundamental obstacles of space and time that separate us. The universe conspires to maintain intelligent species separated by chasms too broad for meaningful engagement. Scientists have computed that our galaxy harbors roughly 400 billion stellar bodies. Yet these innumerable suns are distributed so thinly throughout galactic space that each one exists in magnificent isolation. The nocturnal firmament generates an optical misconception, making stars appear congregated together when they actually inhabit a domain of cosmic solitude. This stellar separation extends throughout our complete galactic vicinity. Even the concentrated central territories of the Milky Way, where stars cluster more compactly than in our external spiral limb, preserve vast vacant spaces between individual suns. The galaxy that appears so abundant and inhabited in telescope imagery actually consists predominantly of vacuum. Pondering these vacant spaces between stellar bodies provides our initial glimpse into the authentic nature of cosmic construction. Substance represents scarce exceptions scattered throughout an overwhelmingly vacant universe. We occupy minuscule havens of material floating in an expanse of nothingness. Yet this galactic emptiness appears positively congested compared to the spaces that divide complete galaxies. Envision tallying every stellar body in our galaxy. Commence with the Sun and proceed outward through the spiral limbs. Enumerate each red dwarf, each blue titan, each binary configuration rotating through space. Sustain a consistent rhythm of 1 star per second without pausing to rest or consume food. You would complete tallying after 12,600 years. Validated observations by space telescopes disclose that our galaxy harbors between 100 billion and 400 billion stellar bodies. The precise figure remains ambiguous because dust formations obstruct our perspective of distant galactic territories. Dark nebulae conceal stellar populations that we can perceive only through infrared emissions. Yet, even the conservative calculation of 100 billion stars overwhelms human comprehension. Each of these stellar furnaces burns with thermonuclear fusion's power. Every second, our sun transforms 4 million tons of substance into pure energy. Multiply this output by hundreds of billions of comparable reactions occurring simultaneously throughout our galaxy. The total energy generation of the Milky Way surpasses human civilization's power utilization by magnitudes that require scientific notation to articulate. Yet this staggering stellar population creates an unsettling awareness. Despite harboring enough suns to energize quadrillions of civilizations, our complete galaxy represents a minuscule portion of cosmic existence. Astronomers categorize the Milky Way as a medium-proportion spiral galaxy. Larger galaxies hold more than 1 trillion stellar bodies. Smaller dwarf galaxies shelter only a few billion stellar furnaces. The probability calculations surrounding galactic star tallies suggest consciousness-altering possibilities for planetary configurations. If even 1% of galactic stars accommodate Earth-like realms, our galaxy harbors billions of potentially habitable planets. Some of these realms might shelter civilizations far more ancient and sophisticated than human society. Others might hold life manifestations so extraterrestrial that we lack terminology to characterize them. Yet what renders these figures truly disturbing is their cosmic insignificance. Every stellar body we have ever witnessed, every planet we might uncover, every possible alien civilization that might exist within our galactic boundaries amounts to less than 1% of the substance in the observable universe. Our galaxy, with all its innumerable worlds, represents a single sand particle on an infinite shoreline. This perspective transformation challenges anthropocentric thinking about our cosmic significance. The ancient conviction that Earth-occupied creation's center appears quaint compared to modern disclosures about galactic magnitudes. We exist on one planet circling one star among hundreds of billions in a galaxy that ranks as perfectly ordinary among trillions of comparable formations. The 400 billion stars of our galaxy burn with energies that dwarf terrestrial phenomena. Their combined illumination output generates the glowing band we witness extending across dark firmaments. Their gravitational engagements shape the spiral limbs where nascent stars continue forming. Their life sequences seed space with heavy elements essential for rocky planets and biological development. All of this cosmic magnificence unfolds within what constitutes our immediate galactic vicinity. The subsequent tier of cosmic arrangement makes our complete stellar metropolis appear like an individual dwelling on an infinite avenue. Gaze toward the Andromeda constellation on any autumn evening. That faint smudge of illumination appears unremarkable among the surrounding stellar bodies. Ancient astronomers cataloged it as a nebula, presuming it belonged to our immediate cosmic vicinity. Modern telescopes expose a truth that should terrify and inspire equally. You are observing another galaxy harboring over 1 trillion stellar bodies. The Andromeda galaxy extends 220,000 light-years across, rendering it more than double the diameter of our Milky Way. These galactic giant shelters enough stellar furnaces to dwarf our immediate star count by magnitudes of 3 or 4. If our galaxy is New York City, Andromeda represents the complete eastern coastline of the United States. Yet validated measurements expose something even more extraordinary. Andromeda is racing toward us at 250,000 miles per hour. This cosmic collision trajectory will culminate in the most spectacular occurrence our solar system will ever experience. Computer models demonstrate that in 4.5 billion years, these two galactic titans will combine in a gravitational choreography lasting several billion years. The collision will restructure both spiral formations into a single elliptical galaxy that astronomers have already nicknamed Milky Way. Throughout this merger, our solar system will likely survive undamaged. The immense spaces between individual stellar bodies mean that stellar collisions remain extremely improbable even during galactic impacts. Instead, gravitational forces will propel our Sun and its planets into fresh orbits around the combined galactic nucleus. Earth might conclude in the external territories of the merged galaxy, gazing upon unfamiliar constellations. Yet what renders Andromeda truly consciousness-altering isn't its dimensions or approaching collision, but what it represents about cosmic separations. The illumination you perceive from Andromeda tonight commenced its expedition 2.5 million years previously when those photons started traveling toward Earth. Primitive human ancestors were just learning to employ stone implements. The galaxy you witness existed before modern humans developed. This temporal displacement means we can never perceive Andromeda as it exists presently. We witness its ancient history preserved in illumination that has traveled across the cosmic emptiness for millions of years. The galaxy approaching us right now might appear completely different from what we witness through telescopes. Even more disturbing is what Andromeda exposes about cosmic magnitudes. Despite being our nearest major galactic companion, it lies so distant that illumination requires millions of years to bridge the interval. This separation represents the smallest meaningful stride beyond our immediate galactic surroundings. Between our galaxy and Andromeda extends an emptiness containing almost nothing except dark substance and dispersed gas formations. This intergalactic space shelters temperatures near absolute zero and densities inferior to the finest vacuum chambers humans can generate. Yet this seemingly vacant gulf teems with invisible forces that govern galactic movements across cosmic duration. The approaching merger of our galaxy with Andromeda will generate fireworks visible from distant galactic communities. Yet, even this cosmic spectacle represents merely a local occurrence in a much larger gravitational theater. Our galaxy doesn't drift alone through cosmic space. The Milky Way belongs to a gravitational family called the Local Group, containing over 50 individual galaxies locked in an eternal cosmic choreography. This galactic vicinity spans roughly 10 million light-years and shelters enough combined mass to bend space and time across vast separations. Validated observations expose that most galaxies in our local group are dwarf configurations containing only a few billion stars each. These cosmic midgets orbit around the two dominant spiral galaxies, our Milky Way and the approaching Andromeda. Like planets circling a binary stellar configuration, these smaller galaxies follow complex orbital trajectories determined by the gravitational interplay between the two largest group constituents. The most prominent dwarf companions are the large and small Magellanic Clouds visible to naked eye observers in the southern hemisphere. These irregular galaxies orbit our Milky Way at separations of 160,000 and 200,000 light-years, respectively. Their proximity renders them laboratories for studying galactic engagements in real time. Scientists have uncovered that our galaxy is actively devouring its smaller companions. Tidal forces generated by the Milky Way's immense gravitational field extract stars and gas from the Magellanic Clouds, supplying material into our galactic disk. This cosmic feeding process has persisted for billions of years, with our galaxy growing larger by absorbing nearby dwarf configurations. Yet this galactic predation exposes something profound about cosmic development. Galaxies don't exist as separated islands floating through vacant space. They inhabit gravitational communities where constant engagements shape their formation and development. The peaceful appearance of nocturnal firmament galaxies conceals violent processes that unfold over cosmic time magnitudes. The local group itself moves through space as a coherent entity. Our complete galactic vicinity travels toward the Virgo cluster at roughly 400 miles per second. This movement carries our immediate collection of galaxies across separations that dwarf individual galactic dimensions. We are passengers on a cosmic vessel sailing through intergalactic space toward gravitational destinations we can barely perceive. Even more extraordinary, the galaxies within our local group are bound together by dark matter halos that extend far beyond their visible boundaries. These invisible gravitational frameworks contain 10 times more mass than all the stars and gas we can witness. Dark matter provides the gravitational adhesive that maintains galactic groups together. Despite space itself expanding, the orbital dynamics within our local group follow precise mathematical principles that govern motion across cosmic magnitudes. Each galaxy traces elliptical trajectories through space, periodically approaching and receding from its companions in cycles lasting billions of years. These gravitational engagements trigger star formation, distort galactic configurations, and redistribute substance across vast separations. Comprehending our galactic vicinity demands thinking in time magnitudes that surpass human experience. The current configuration of the local group represents just one instant in a cosmic development spanning tens of billions of years. Galaxies merge, separate, and merge again in patterns too gradual for human observation, yet recorded in the movements we measure today. This immediate gravitational choreography represents merely the smallest organizational component in a cosmic hierarchy that grows increasingly complex. Galaxy clusters represent the most massive gravitationally bound formations in the universe. These cosmic municipalities contain thousands of individual galaxies held together by forces so powerful they distort space and time across millions of light-years. The nearest major cluster, called Virgo, harbors over 1,300 galaxies and lies 54 million light-years from our local group. Validated measurements expose that galaxy clusters shouldn't exist according to the visible substance we witness. The combined gravitational attraction of all stars and gas in cluster galaxies cannot account for the tremendous forces needed to maintain these formations together. Galaxies within clusters move at velocities approaching 3 million miles per hour. Such velocities should have dispersed cluster constituents across cosmic space billions of years previously. The resolution to this enigma required discovering that most cluster mass remains completely invisible. Dark matter outweighs visible stars and gas by proportions of 10:1 throughout galaxy clusters. This enigmatic substance reveals itself only through gravitational influences on illumination and substance, generating a cosmic framework we can map yet cannot directly witness. Scientists employ gravitational lensing to investigate dark matter distribution in galaxy clusters. Massive clusters bend space so severely that they function like cosmic magnifying instruments, distorting the appearance of background galaxies. The magnitude of distortion discloses how much invisible mass clusters harbor. These measurements validate that dark matter dominates cluster formation despite remaining undetectable to any instrument humans have constructed. The most spectacular demonstration of dark matter evidence comes from the Bullet cluster, where two galaxy clusters collided at velocities exceeding 10 million miles per hour. Throughout this cosmic collision, the visible gas formations engaged and decelerated, yet the dark matter components passed through each other unchanged. Gravitational lensing maps display dark matter and visible substance separated by millions of light-years, providing direct confirmation that invisible mass exists independently of stars and gas. Galaxy clusters also serve as cosmic laboratories for investigating extreme physics. The hot gas between cluster galaxies reaches temperatures of 100 million degrees Celsius, hot enough to strip electrons from atoms and generate plasma that glows in X-ray wavelengths. This superheated material holds more mass than all the cluster galaxies combined, yet remains invisible to optical telescopes. The space between cluster galaxies teems with high-energy particles accelerated to near light velocity by magnetic fields spanning millions of light-years. These cosmic ray particles generate radio emissions detectable by specialized telescopes, exposing magnetic formations that connect distant galaxies within clusters. Yet what renders galaxy clusters truly consciousness-altering is their role in cosmic development. Clusters represent the terminal points of gravitational collapse in our universe. Dark matter commenced clumping together shortly after the Big Bang, eventually generating the gravitational wells where galaxies formed. Over cosmic duration, these galactic collections merged into increasingly massive clusters. The largest known galaxy cluster, called El Gordo, contains the mass of 3 quadrillion suns and spans 15 million light-years. This cosmic monster lies 7 billion light-years distant, meaning we witness it as it existed when our solar system was just forming. Galaxy clusters form nodes in an even larger cosmic formation that resembles a three-dimensional spider's web. Superclusters represent the largest validated gravitational formations in our universe. These cosmic constructions extend across separations so immense that illumination requires hundreds of millions of years to traverse them. Our local group belongs to the Laniakea supercluster, a gravitational collection spanning 500 million light-years and containing over 100,000 galaxies. The discovery of superclusters revolutionized our comprehension of cosmic arrangement. Instead of being randomly dispersed through space, galaxies organize themselves in vast networks connected by filaments of dark matter and gas. These cosmic highways channel substance across separations that dwarf individual galaxy clusters, generating a hierarchical formation that extends to the largest observable magnitudes. Scientists mapped our immediate supercluster by tracking the peculiar movements of thousands of galaxies. Despite cosmic expansion pushing distant galaxies apart, gravity causes nearby galaxies to move toward territories of higher concentration. By measuring these gravitational flows, astronomers disclosed that our Milky Way and millions of neighboring galaxies are all streaming toward a massive gravitational attractor. This attractor, called the Great Attractor, holds the combined mass of tens of thousands of galaxies concentrated in a territory obscured by dust formations in our galactic plane. The gravitational attraction from this cosmic monster influences galaxy movements across hundreds of millions of light-years, generating currents in the cosmic web that carry complete galaxy clusters toward areas of increasing concentration. Yet the Great Attractor itself represents only a small component of an even larger formation. Recent observations disclose that Laniakea forms part of an enormous complex of superclusters spanning more than 1 billion light-years. This formation, called the Pisces Cetus supercluster complex, may represent the largest coherent formation in the observable universe. The ramifications of supercluster arrangement challenge our comprehension of cosmic development. These vast formations formed through gravitational processes that demanded billions of years to generate the patterns we witness today. Dark matter commenced clumping together when the universe was less than 1% of its current age, eventually generating the framework along which visible substance organized itself. Supercluster boundaries remain difficult to define precisely because they blend into neighboring formations. Unlike galaxy clusters, which are clearly bound by gravity, superclusters represent looser associations that may be dispersing due to cosmic expansion. Some territories within superclusters continue collapsing under their own gravity, while other areas are being stretched apart by dark energy. The configuration of superclusters resembles biological formations more than geometric objects. Laniakea appears like a vast sheet with tendrils extending in multiple directions, similar to neural networks in the human brain. This resemblance may not be coincidental, as both systems organize through processes that generate branching hierarchical formations. Witnessing supercluster formation demands telescopes capable of mapping millions of galaxies across vast separations. The Sloan Digital Sky Survey generated three-dimensional maps exposing supercluster arrangement by measuring precise separations to over 1 million galaxies. These surveys demonstrate that superclusters connect to form even larger formations resembling cosmic scaffolding. The cosmic web that emerges from supercluster mapping appears like soap bubbles floating in space, with galaxies concentrated along bubble boundaries and enormous voids occupying bubble interiors. This soap bubble architecture extends throughout the observable universe. Retreat far enough from the universe and a stunning pattern materializes. Galaxies don't scatter randomly through space, but organize themselves into a vast three-dimensional network resembling soap foam floating in cosmic darkness. This formation, called the cosmic web, represents the largest scale arrangement of substance in our universe. Computer models validate that this web-like architecture formed naturally through gravitational processes commencing shortly after the Big Bang. Dark matter started clumping together when the universe was only a few 100,000 years old, generating gravitational seeds that eventually grew into the cosmic framework we witness today. The cosmic web comprises 4 distinct components functioning together across billions of light-years. Dense nodes mark the intersections where galaxy clusters form. Filaments extend between nodes like cosmic highways, channeling substance across vast separations. Walls form sheet-like formations where filaments intersect. Between these formations lie cosmic voids containing almost nothing except vacant space. Scientists have mapped this cosmic construction by witnessing millions of galaxies and measuring their three-dimensional positions in space. The resulting surveys disclose that galaxies trace out the boundaries of enormous bubbles, with void territories occupying bubble interiors. This foam-like formation extends throughout the observable universe with remarkable consistency. The magnitude of cosmic web components defies human intuition. Individual filaments extend across hundreds of millions of light-years while maintaining widths of only 20 million light-years. These cosmic threads appear impossibly thin when viewed at universal magnitudes. Yet they harbor enough substance to fuel billions of galaxies. Substance flows along filaments like water through cosmic plumbing, supplying galaxy formation in the densest territories. Galaxy clusters form where multiple filaments intersect, generating gravitational traffic congestion that traps substance for billions of years. These cosmic crossroads represent the busiest communities in the universe, where galaxy engagements trigger star formation and supermassive black hole growth. The most massive clusters mark the locations where the cosmic web reaches its highest concentration. Yet what renders the cosmic web truly extraordinary is its dynamic nature. This formation continues developing as cosmic expansion stretches the universe and dark energy accelerates the separation between distant territories. Filaments that currently connect distant superclusters will eventually snap as space expands beyond the reach of gravitational forces. The gas threading through cosmic web filaments remains mostly invisible to optical telescopes, yet glows faintly in ultraviolet and X-ray wavelengths. This intergalactic medium holds more mass than all the stars in the universe combined. Yet it spreads so thinly that cubic meters of this material hold only a few atoms. Recent observations have detected the warm-hot intergalactic medium predicted to fill cosmic web filaments. This material reaches temperatures of millions of degrees while maintaining densities barely above the cosmic vacuum. Finding this elusive component demanded specialized X-ray telescopes capable of detecting extremely faint emissions from hot gas. The cosmic web extends beyond our current observational capabilities, suggesting that the formations we can map represent only a small portion of universal arrangement. Hidden within this web lie cosmic voids so vacant they challenge our comprehension of space itself. Envision a sphere of space 300 million light-years across, harboring almost nothing. No galaxies shine within this cosmic wasteland. No stars illuminate its darkness. No planets orbit through its emptiness. This vacant realm called a cosmic void represents one of the most enigmatic territories in our universe. The Boötes void discovered in 1977 spans 330 million light-years in diameter while harboring fewer than 60 known galaxies. If our local group existed within this cosmic bubble, the nearest major galaxy would lie so distant that it would appear as a barely detectable smudge in our most powerful telescopes. Validated observations expose that cosmic voids occupy roughly 80% of universal volume. These enormous vacant territories separate the cosmic web filaments where galaxies cluster together. Despite their vast dimensions, voids harbor less than 15% of the average substance concentration found elsewhere in the universe. Scientists initially struggled to clarify how such vacant territories could exist. Early theories suggested that voids formed through explosive occurrences that cleared substance from huge volumes of space. Modern research exposes that voids represent natural consequences of cosmic web formation. As substance clumped together along filaments and walls, it drained away from the territories that became voids. The emptiness within cosmic voids generates circumstances unlike anywhere else in the observable universe. Temperatures inside voids hover just a few degrees above absolute zero. Densities fall so low that individual hydrogen atoms may be separated by separations measured in miles rather than microscopic magnitudes. These circumstances approach the perfect vacuum that physicists can generate only in specialized laboratory chambers. Yet voids aren't completely vacant. They harbor invisible dark matter that forms the gravitational framework connecting them to surrounding formations. Computer models demonstrate that void territories contain dark matter filaments too tenuous to gravitationally trap normal substance. These invisible threads generate a web within the web, extending cosmic arrangement into apparently vacant space. Galaxies that do exist within voids follow different evolutionary trajectories than their counterparts in denser territories. Void galaxies tend to be smaller, bluer, and more actively forming stars than typical galaxies. The isolation within voids protects these rare galaxies from gravitational engagements that would disrupt their star formation processes. The largest known void, called the Giant Void or KBC void, spans 1.8 billion light-years across. This cosmic wasteland holds so little substance that if our Milky Way existed at its center, we would not have uncovered the existence of other galaxies until the 1960s. The nocturnal firmament would appear almost completely dark, except for our immediate galactic companions. Cosmic voids also affect the cosmic microwave background radiation left over from the Big Bang. Photons passing through void territories experience slightly different gravitational influences than those traveling through denser areas. These subtle temperature variations provide another way to map void locations across cosmic separations. The expansion of space preferentially affects void territories, causing them to grow larger over duration, while substance continues draining towards surrounding formations. Yet even these enormous vacant territories appear small compared to the largest solid formations astronomers have uncovered. The largest solid formations in the observable universe extend across separations so immense they challenge the fundamental limitations of what cosmic physics should permit. These enormous walls and sheets of galaxies span billions of light-years while maintaining thicknesses of only 20 million light-years, generating cosmic construction that resembles impossibly thin membranes floating through space. The first galactic wall uncovered by astronomers, called the Coma Wall, extends 500 million light-years in length while measuring only 16 million light-years thick. This cosmic formation harbors thousands of galaxies arranged in a thin sheet that would appear edge-on as a barely visible line if viewed from the side. The wall lies 300 million light-years from our local group, rendering it a prominent feature in our cosmic vicinity. Yet, validated observations have disclosed far larger formations that push the boundaries of theoretical predictions. The Sloan Great Wall spans 1.3 billion light-years across, rendering it one of the largest known formations in the universe. This cosmic barrier holds hundreds of thousands of galaxies organized into a coherent pattern that extends across roughly 1% of the observable universe diameter. Even more extraordinary is the Hercules Corona Borealis Great Wall, discovered through mapping gamma-ray bursts from distant galaxies. This formation measures 10 billion light-years across, rendering it so large that illumination requires more than 1/10 of the universe's age to travel from one extremity to the other. The existence of such enormous formations challenges theoretical models of how cosmic arrangement should develop. These galactic walls form where cosmic web filaments intersect across vast separations. Computer models demonstrate that dark matter naturally generates sheet-like formations when gravitational forces pull substance together from multiple directions simultaneously. Normal substance follows these dark matter frameworks, generating the galaxy concentrations we witness. The thinness of cosmic walls generates gravitational influences that influence galaxy development across enormous separations. Galaxies within walls experience enhanced tidal forces that can trigger star formation bursts or strip substance from smaller neighboring configurations. The gravitational surroundings within walls differs significantly from circumstances in cosmic voids or dense cluster cores. Scientists employ cosmic walls as laboratories for investigating large-scale formation generation. The precise arrangement of galaxies within walls provides clues about the initial circumstances that existed shortly after the Big Bang. Comparing witnessed wall formations with computer models helps test theories about dark matter properties and cosmic development. Yet what renders these walls truly consciousness-altering is their role in universal arrangement. Despite their enormous dimensions, cosmic walls represent intermediate-scale formations between superclusters and the largest detectable patterns in galaxy distribution. They form components of even larger organizational schemes that extend toward the limitations of observational capability. The discovery of cosmic walls also exposes the dynamic nature of large-scale formation. These enormous features continue developing as cosmic expansion stretches the universe. Walls that appear solid today will eventually fragment as dark energy overcomes gravitational forces, maintaining their components together. Some cosmic walls may extend beyond our current observational boundary, connecting to formations we cannot yet perceive. This possibility hints at organizational patterns spanning the complete observable universe. Direct the most powerful telescope ever constructed toward any minuscule patch of apparently vacant firmament. Maintain the camera open for days, collecting every photon that arrives from that cosmic direction. The resulting image will expose something that should fundamentally transform how you think about existence. That minuscule territory no larger than a sand particle held at arm's length harbors thousands of galaxies. The Hubble ultra-deep field generated by combining 800 separate images with 11 days of total exposure duration disclosed over 10,000 galaxies in a patch of firmament covering just 1/13 millionth of the celestial sphere. Each galaxy in this cosmic census holds billions of stellar bodies, many likely accommodating planetary configurations where life might exist. Validated analysis of deep field observations permits astronomers to compute the total galaxy population within our observable universe. The most recent calculations based on data from the Hubble and James Webb Space Telescopes suggest that 2 trillion galaxies populate the cosmic volume we can currently perceive. 2 trillion represents a figure that overwhelms human comprehension. If you could witness one galaxy per second without pausing, you would require 63,000 years to perceive them all. Recorded completely, this figure demands 13 zeros, 2 million galaxies dispersed throughout observable space. Each of these galactic islands harbors its own stellar populations. Conservative calculations suggest that the typical galaxy shelters 100 billion stellar bodies. Multiplying galaxy tally by stellar populations yields a cosmic census surpassing 10 to the 24th power individual stars. This figure exceeds the tally of sand particles on every shoreline on Earth. Yet what renders this galactic abundance truly disturbing is how it redistributes significance in the cosmic hierarchy. Our complete local group harboring over 50 galaxies represents less than 1/50 billionth of the total galactic population. The Milky Way with its 400 billion stars ranks as utterly typical among the 2 trillion cosmic companions sharing our universe. Recent observations suggest that galaxy tallies may actually underestimate universal populations. Improved detection methods continue uncovering faint dwarf galaxies that previous surveys overlooked. These minuscule galactic configurations containing only millions of stars each may outnumber large spiral galaxies by proportions of 10 to 1. Deep field observations also disclose galaxies at various stages of cosmic development. Distant galaxies appear as they existed billions of years previously when the universe was young and star formation rates surpassed current levels. These ancient configurations display different formations and compositions than nearby modern galaxies, providing glimpses into cosmic chronicles. The distribution of galaxies throughout space follows the cosmic web pattern, extending to the largest observable magnitudes. Galaxy tallies remain roughly constant in all directions astronomers examine, validating that universal formation appears uniform when viewed from cosmic separations. This uniformity suggests that our observable volume represents a fair sample of universal contents. Yet every galaxy survey pushing deeper into space exposes additional cosmic companions previously hidden beyond detection limitations. Each improvement in telescope sensitivity adds billions of galaxies to the cosmic census. The 2 trillion galaxies we can currently perceive may represent only a small portion of total galactic populations. Stroll along any ocean coastline and scoop up a handful of sand. Tally the individual particles between your fingers. A typical handful harbors roughly 10,000 minuscule fragments of rock and shell, each representing millions of years of erosion and weathering. Now expand your tally to encompass every shoreline on Earth. Include the Caribbean islands, the Mediterranean coast, the Pacific atolls, and the Arctic shores. Tally every particle of sand on every shoreline surrounding every continent and every island on our planet. Scientists calculate that Earth's shorelines harbor approximately 7 quintillion particles of sand. Recorded with zeros, this figure spans 20 digits. 7 million individual particles. This astronomical tally of earthly sand particles pales in comparison to cosmic stellar populations. Validated observations disclose that the observable universe harbors more stellar bodies than particles of sand on Earth. The 2 trillion galaxies we can perceive shelter enough stellar furnaces to dwarf our planetary sand tally by magnitudes of thousands. Every time you retrieve a handful of shoreline sand, remember that cosmic space harbors thousands of stars for each particle between your fingers. Yet this comparison becomes even more staggering when we contemplate planetary populations. Modern exoplanet surveys suggest that most stars accommodate at least one planet, with many configurations containing multiple worlds. If conservative calculations prove accurate, the observable universe harbors more planets than sand particles on Earth multiplied by Earth's total quantity of atoms. Each of these innumerable worlds represents a unique experiment in planetary development. Rocky planets orbit in zones where liquid water could exist. Gas giants dominate external planetary territories. Ice worlds shelter subsurface oceans. Desert planets bake under intense stellar radiation. The variety of planetary surroundings surpasses anything science fiction has conceived. The probability calculations surrounding these figures suggest consciousness-altering ramifications for life in the universe. Even if life emerges on just one planet per million suitable worlds, the cosmos should teem with biological activity. Some civilizations might have developed billions of years before Earth formed. Others might possess technologies that render human achievements appear primitive. Yet the vast separations dividing star configurations generate isolation that prevents most worlds from ever communicating with their cosmic companions. The velocity of light barrier ensures that civilizations separated by thousands of light years can never establish meaningful contact. Each inhabited world develops in cosmic solitude, unaware of the innumerable other experiments in intelligence occurring throughout the universe. This isolation clarifies why our nocturnal firmament appears so quiet despite the enormous quantity of potential cosmic companions. Radio signals from extraterrestrial civilizations would demand centuries or millennia to cross the spaces between star configurations. By the time communications arrive, the civilizations that transmitted them might have developed beyond recognition or vanished entirely. The stellar census also exposes something profound about cosmic viewpoint. Every human who has ever lived exists on one planet, circling one star among more stellar furnaces than sand particles on Earth. Yet this incredible stellar abundance represents just the commencement of cosmic magnitudes that dwarf even these consciousness-numbing figures. The universe you can perceive tonight has boundaries, not physical walls marking space's termination, but fundamental limitations imposed by illumination's velocity and the age of cosmic duration. These boundaries define what astronomers call the observable universe, a sphere of space harboring everything we can potentially perceive using any technology humans might ever develop. Validated measurements disclose that this observable sphere measures 93 billion light-years in diameter. This separation represents the maximum extent of space from which illumination has had duration to reach Earth since the universe commenced. Beyond this cosmic boundary lies a realm perpetually hidden from human observation. The computation behind this cosmic boundary demands comprehending both light travel duration and cosmic expansion. Illumination from the most distant observable objects commenced its expedition 13.8 billion years previously when the universe was only 380,000 years old. Yet throughout the expedition duration, cosmic expansion stretched the space between origin and destination. Objects that emitted illumination 13.8 billion years previously now lie 46.5 billion light-years distant due to this cosmic stretching. Illumination that departed distant galaxies when they were relatively proximate arrives at Earth after those same galaxies have been transported to much greater separations by expanding space. This generates one of the most counterintuitive realities about cosmic observation. The most distant galaxies we can perceive appear as they existed when the universe was young and small. Yet those same galaxies currently exist far beyond our observational boundary, developed into forms we can never witness directly. The boundary of the observable universe coincides with the cosmic microwave background radiation, the afterglow from when atoms first formed in space became transparent to illumination. This radiation provides a baby picture of the universe captured when it was less than 1% of its current age. Yet what renders the observable boundary truly consciousness-altering is its personal nature. Every observer in the universe possesses their own unique observable sphere centered on their location. Extraterrestrial astronomers in distant galaxies witness cosmic volumes that overlap with ours in some territories while extending into space we can never perceive. The observable universe continues growing larger every day as illumination from increasingly distant territories reaches Earth for the initial time. Each second, our cosmic visibility increases by 1 light second in every direction. Over cosmic duration, this gradual expansion of observational range exposes nascent galaxies emerging from beyond the cosmic boundary. Yet this growing visibility cannot persist perpetually. Cosmic expansion will eventually overcome light travel, causing distant galaxies to cross permanently beyond our observational reach. The observable universe will commence shrinking as expansion transports cosmic companions across the cosmic boundary, never to be perceived again. Current observations suggest that we inhabit during a golden age of cosmic visibility. The observable universe currently harbors more galaxies than at any previous instant in cosmic chronicles, yet fewer than will be visible in the far future when expansion isolates us from increasingly distant companions. This cosmic boundary raises profound questions about the nature of space beyond our observational limitations. The universe we cannot perceive may be vastly larger than the cosmic volume available to human observation. Space itself moves more rapidly than illumination. This statement appears to violate Einstein's cosmic velocity limitation. Yet validated observations prove that the fabric of spacetime expands at rates that dwarf the velocity of photons racing through the cosmic emptiness. Einstein's relativity prohibits substance and energy from traveling more rapidly than illumination through space. Yet space itself confronts no such restriction. The universe can stretch its own fabric at any rate without violating physical principles. Throughout cosmic inflation, space expanded so rapidly that territories separated by subatomic separations grew to cosmic magnitudes in less than a second. This distinction between movement through space and expansion of space generates consciousness-altering consequences for cosmic observation. Galaxies at the boundary of our observable universe are currently racing away from us at velocities approaching 3 times illumination's velocity. Yet these same galaxies aren't actually moving through space at relativistic velocities. Instead, expanding space transports distant galaxies along like passengers on a cosmic escalator. The galaxies themselves maintain relatively modest velocities through immediate space. Yet the cumulative influence of expansion across billions of light-years generates apparent recession velocities that surpass light velocity. Hubble's principle quantifies this cosmic expansion through a simple relationship between separation and recession velocity. Galaxies twice as distant recede twice as rapidly. 3 times the separation means 3 times the velocity. This linear relationship persists until recession velocities surpass illumination's velocity at separations exceeding 14 billion light-years. The discovery of accelerating cosmic expansion won the 2011 Nobel Prize in Physics. Observations of distant supernovae disclosed that expansion rates are increasing over duration rather than decelerating as astronomers anticipated. Dark energy, comprising 68% of universal contents, drives this accelerating expansion against gravitational forces. Current expansion rates suggest that space doubles in dimensions every 10 billion years. This may appear gradual compared to human duration magnitudes, yet cosmic expansion operates across such vast separations that its influences accumulate to tremendous velocities at large magnitudes. The acceleration of cosmic expansion means that most galaxies we can currently witness will eventually disappear beyond our cosmic boundary. In approximately 2 trillion years, only galaxies within our local group will remain visible to future astronomers. The nocturnal firmament will appear almost vacant, except for our galactic companions. Yet expansion rates may persist increasing until dark energy overwhelms all other forces in the universe. Theoretical models suggest that accelerating expansion could eventually tear apart galaxies, star configurations, and even atomic nuclei in an occurrence called the Big Rip. This cosmic destruction would occur approximately 22 billion years from now. Yet the current expansion rate generates opportunities as well as isolation. Space telescopes can witness galaxies at separations where recession velocities approach light velocity. These observations provide glimpses into cosmic circumstances when the universe was young and stellar formation rates surpassed current levels. The expanding universe also permits astronomers to perceive farther backward in duration by witnessing increasingly distant objects. Each improvement in telescope sensitivity exposes earlier cosmic epochs. Yet, expansion transports most of the universe beyond our permanent observational reach. The space we cannot perceive may extend infinitely in all directions. At the very boundary of observable space glows a wall of ancient illumination, marking the boundary between visible cosmos and unknowable emptiness. This cosmic microwave background radiation represents the oldest illumination in the universe. Emitted when atoms first formed in space became transparent 13.8 billion years previously. Before this instant called recombination, the universe harbored too much free energy for stable atoms to exist. Protons and electrons remained separated in a cosmic mixture so dense that illumination could travel only microscopic separations before scattering off charged particles. The universe was literally opaque, like existing inside a glowing fog so thick that nothing could be perceived beyond arm's length. When cosmic expansion cooled temperatures below 3,000 degrees Celsius, protons and electrons combined into hydrogen atoms for the initial time. This removed the charged particles that scattered illumination, permitting photons to travel freely through space. The universe became transparent in a cosmic instant, releasing radiation that continues traveling toward us today. Validated observations perceive this background radiation arriving from every direction in space with extraordinary uniformity. Advanced satellites measure temperature variations of only a few millionths of a degree across the cosmic microwave background. These minuscule fluctuations represent quantum uncertainties from the universe's birth, amplified by cosmic expansion into the seeds that eventually became galaxies. The cosmic microwave background serves as humanity's baby picture of the universe. We witness this radiation as it existed when cosmic duration measured only 380,000 years compared to the current age of 13.8 billion years. The patterns frozen in this ancient illumination expose circumstances when the initial atoms formed and cosmic formation commenced emerging from primordial smoothness. Yet this radiation wall also marks the absolute limitation of electromagnetic observation. No telescope can perceive beyond the cosmic microwave background because no illumination existed in observable form before recombination occurred. Earlier cosmic epochs remain hidden behind this wall of ancient radiation, accessible only through indirect detection of gravitational waves or neutrino emissions. The cosmic microwave background surrounds Earth like the inner surface of an enormous sphere centered on our location. Every point on this sphere lies exactly 46.5 billion light-years distant, representing the maximum separation from which illumination has had duration to reach us since the universe became transparent. Yet this observational boundary moves outward every day as cosmic expansion transports the background radiation origin to greater separations. The sphere of cosmic microwave background emission grows larger continuously, yet the radiation itself grows fainter and cooler as expansion stretches its wavelengths toward longer, less energetic frequencies. In the far future, cosmic expansion will stretch this background radiation beyond the detection capabilities of any conceivable instrument. The cosmic microwave background will fade into undetectable whispers, removing even this ancient signpost marking the boundary of observable space. This radiation boundary raises profound questions about cosmic contents beyond our observational reach. The universe certainly existed before recombination occurred, yet circumstances during earlier epochs remain largely theoretical. Whatever lies beyond the cosmic microwave background wall may dwarf our observable universe in ways we cannot conceive. Beyond the cosmic microwave background lies a universe we can never perceive yet know must exist. This hidden realm extends backward through cosmic duration to periods when temperatures surpassed nuclear fusion cores and forward through space to separations that may persist infinitely in all directions. Theoretical physics provides glimpses into cosmic circumstances before the universe became transparent. Throughout the initial 380,000 years, temperatures surpassed those found in stellar interiors. Substance existed as plasma so hot that atomic nuclei could not retain electrons. The complete universe glowed more brilliantly than any star's surface. Even earlier epochs push physics to its theoretical limitations. Throughout the initial 3 minutes after the Big Bang, cosmic temperatures permitted nuclear fusion to occur throughout space. Protons and neutrons combined into light elements, generating the cosmic abundance of hydrogen and helium we witness today. This primordial nucleosynthesis occurred when the universe was smaller than our solar system yet harbored all the substance we can currently witness. The initial second of cosmic duration remains largely enigmatic. Theoretical models suggest that fundamental forces separated during this period as expansion cooled the universe below energy magnitudes where particle physics breaks down. Gravity separated initially, followed by the strong nuclear force, then electromagnetic and weak nuclear forces. Yet validated observations suggest that our universe extends far beyond the cosmic microwave background in spatial dimensions as well as temporal chronicles. The flatness and uniformity of space indicate that cosmic inflation expanded the universe by enormous magnitudes during its initial tiny fraction of a second. This expansion stretched quantum fluctuations to cosmic magnitudes while generating space much larger than our observable volume. If inflation theories prove accurate, our observable universe represents an infinitely decimally small portion of total cosmic volume. The territory that became our observable sphere was smaller than a proton before inflation commenced. Expansion increased its dimensions by magnitudes surpassing 10 to the 26th power. Yet this inflated volume still constitutes only a minuscule bubble within a vastly larger cosmic formation. Current models suggest that distinct territories of this larger universe may have developed under distinct physical circumstances. Areas beyond our cosmic boundary might have experienced distinct inflation rates, generating domains where physical constants adopt distinct values. Electrons might possess distinct masses. Illumination might travel at distinct velocities. Gravity might operate with distinct strengths. These variations could generate cosmic territories where stars form distinctly, where chemistry follows alternative principles, where life develops through unimaginable processes. Each domain might represent a unique experiment in physics, isolated from neighboring territories by expansion too rapid for communication. Some theoretical models propose that cosmic inflation persists in territories beyond our observable volume. Nascent space constantly forms through eternal inflation, generating infinite quantities of observable universe-sized bubbles within an ever-growing cosmic formation. This possibility suggests that our observable universe, harboring 2 trillion galaxies and more stars than sand particles on Earth, represents merely one small chamber in an infinite cosmic mansion. The authentic magnitude of existence may extend far beyond human comprehension or observational capability. Scientists employing advanced statistical analysis have computed that our observable universe may represent less than 1% of total cosmic volume. Bayesian mathematical models suggest the authentic universe extends at least 250 times farther than the cosmic boundary we can perceive, rendering the hidden cosmos vastly larger than anything humans will ever witness. This computation relies on measuring the curvature of space across the largest observable magnitudes. If the universe was smaller than our observable volume, space would display detectable curvature like a sphere's surface. Yet precise measurements of the cosmic microwave background expose that space appears perfectly flat across billions of light-years. Flat geometry indicates that the universe extends far beyond our observational limitations. The territory we can perceive represents a minuscule patch within a cosmic formation so large that its curvature remains undetectable across separations spanning our complete observable sphere. This resembles standing on Earth's surface where the ground appears flat because our planet is much larger than our immediate boundary. Conservative calculations based on cosmic flatness suggest the universe measures at least 7 trillion light-years in diameter. This minimum dimension surpasses our observable universe by magnitudes of 75, meaning that for every galaxy we can perceive, at least 5,000 comparable galaxies exist beyond our cosmic boundary. Yet theoretical models propose even larger possibilities. Eternal inflation theory suggests that nascent space constantly forms through quantum processes, generating infinite quantities of observable universe-sized territories within an ever-expanding cosmic formation. Each territory would harbor its own collection of galaxies, stars, and planets isolated from neighboring domains by expansion too rapid for illumination to bridge. This hidden cosmos raises profound questions about cosmic uniqueness. If the universe extends far beyond our observation, then circumstances similar to those in our cosmic vicinity must be repeated innumerable times throughout the larger formation. Planets identical to Earth might exist in distant cosmic domains. Civilizations equivalent to human society might develop around comparable stellar configurations. The probability calculations surrounding an infinite universe suggest that every possible arrangement of substance must occur somewhere within the hidden cosmic volume. This includes not just Earth-like worlds, yet perfect duplicates of our complete observable universe repeated throughout infinite space. Yet this vast hidden realm remains perpetually inaccessible to human observation or investigation. Even traveling at light velocity, explorers could never reach territories beyond our cosmic boundary because expansion transports them away more rapidly than any signal can propagate. The hidden universe represents a realm we can theorize about yet never directly investigate. Recent observations of cosmic microwave background polarization provide indirect evidence for the larger cosmic formation. Patterns in ancient illumination suggest that our observable territory connected to neighboring domains during cosmic inflation. These connections left subtle imprints that surviving advanced instruments can perceive. The discovery that our observable universe represents a minuscule fraction of cosmic totality fundamentally transforms our viewpoint on human significance. Every stellar body we can perceive, every galaxy we can witness, every possible extraterrestrial civilization within our cosmic boundary exists within less than 1% of universal content. The remaining 99% of existence lies perpetually beyond human knowledge. Something invisible is tearing the universe apart. Dark energy, comprising 68% of cosmic contents, accelerates space's expansion with a force so powerful that it overwhelms gravity across separations larger than galaxy clusters. This enigmatic component of reality pushes distant galaxies away from us at ever-increasing velocities. The discovery of cosmic acceleration shocked astronomers who anticipated gravitational forces to gradually decelerate universal expansion. Two autonomous research teams investigating distant supernovae in 1998 found that cosmic expansion was accelerating rather than decelerating. This observation earned the 2011 Nobel Prize in Physics and revolutionized our comprehension of cosmic development. Dark energy behaves unlike any known form of substance or radiation. While normal substance becomes less dense as space expands, dark energy maintains constant concentration throughout cosmic growth. This means that dark energy's influence grows stronger over duration as space increases in volume, while dark energy concentration remains unchanged. Current expansion rates indicate that space doubles in dimensions every 10 billion years. This may appear gradual, yet dark energy's constant concentration means that its gravitational repulsion doubles every occasion space doubles. Cosmic acceleration therefore increases exponentially, generating runaway expansion that will eventually overcome all other forces in the universe. Validated observations demonstrate that dark energy currently dominates cosmic dynamics at magnitudes larger than several hundred million light-years. Within this separation, gravitational attraction between substance concentrations can overcome dark energy repulsion. Beyond this magnitude, dark energy wins every gravitational battle, pushing cosmic formations apart despite their mutual attraction. This cosmic tug-of-war determines the fate of every galaxy we can witness. Galaxies within our local group remain gravitationally bound despite cosmic expansion. Yet galaxies in distant clusters are being transported away by dark energy at velocities that will eventually surpass light velocity. Most cosmic companions will disappear beyond our observational boundary within 2 trillion years. The nature of dark energy remains one of the greatest enigmas in physics. Leading theories suggest it represents vacuum energy arising from quantum fluctuations in vacant space. Alternative models propose that dark energy varies over duration or that gravity itself behaves distinctly at cosmic magnitudes. Some theoretical computations suggest that dark energy acceleration will persist increasing until it overcomes nuclear forces maintaining atomic nuclei together. This Big Rip scenario would tear apart galaxies, star configurations, and eventually atoms themselves approximately 22 billion years from now. Yet dark energy also generates opportunities for cosmic observation. The accelerating expansion permits astronomers to perceive farther backward in cosmic duration by witnessing galaxies at separations where recession velocities approach light velocity. These observations expose cosmic circumstances when star formation rates surpassed current levels. Dark energy measurements also provide tests of Einstein's general relativity across cosmic magnitudes. Precise observations of cosmic acceleration help determine whether gravity behaves as Einstein predicted or demands modifications at the largest observable separations. The discovery of dark energy fundamentally transformed our comprehension of cosmic composition. The universe comprises primarily of components we cannot directly perceive. Dark energy and dark matter together comprise 95% of cosmic contents. Normal substance represents only 5% of universal reality. Most galaxies visible in tonight's firmament will vanish from human view within the next 2 trillion years. Dark energy acceleration will transport these cosmic companions beyond our observational boundary, leaving future astronomers with an almost vacant nocturnal firmament containing only galaxies within our local group. This cosmic isolation has already commenced. Galaxies at separations exceeding 14 billion light-years currently recede more rapidly than light velocity due to cosmic expansion. Illumination departing these distant configurations can never reach Earth because space expands more rapidly than photons can travel through it. We witness these galaxies only because their illumination commenced the expedition toward us when they were much closer. Computer models expose the timeline of cosmic loneliness. Within 50 billion years, the Virgo cluster will disappear beyond our cosmic boundary. The most distant galaxies we can currently witness will fade from view as their illumination becomes too redshifted to perceive. Within 100 billion years, only local group galaxies will remain visible to observers in our cosmic vicinity. Yet even this reduced galactic family confronts internal transformations. The approaching collision between our Milky Way and Andromeda will restructure the local group within 5 billion years. Smaller galaxies will be disrupted or absorbed throughout this merger, reducing the quantity of distinct galactic configurations in our immediate vicinity. Future astronomers inhabiting the merged Milky galaxy will occupy profoundly distinct cosmic surroundings. Their nocturnal firmament will harbor no external galaxies beyond their immediate merged configuration. Deep space will appear vacant except for the cosmic microwave background radiation, which itself will become too faint to perceive as cosmic expansion stretches its wavelengths beyond instrumental sensitivity. This cosmic isolation generates a disturbing possibility for future science. Astronomers inhabiting billions of years from now may possess no evidence that other galaxies ever existed. The expansion chronicles of the universe will be erased from observational records. The Big Bang Theory might never be uncovered because the evidence supporting it will have disappeared beyond detection limitations. Yet current observations suggest that cosmic acceleration may increase over duration. If dark energy concentration grows, as some theoretical models predict, the expansion rate could accelerate until it overcomes gravitational forces within individual galaxies. Stellar bodies would be torn away from galactic nuclei. Planetary configurations would be disrupted. Eventually, even atomic nuclei could be ripped apart. This scenario, called the Big Rip, represents the ultimate triumph of dark energy over all other forces in nature. It would occur approximately 22 billion years from now if current acceleration trends persist increasing. Yet less extreme models suggest that dark energy might remain constant or even decrease over cosmic duration. These possibilities would prevent the Big Rip while still isolating distant galaxies beyond observational reach. The discovery of cosmic acceleration fundamentally transformed our comprehension of universal fate. Instead of eventually collapsing backward toward a big crunch, the universe appears destined for eternal expansion and increasing isolation. We inhabit during a golden age of cosmic visibility that will never return. Earth occupies the exact center of the observable universe. This statement appears to place humanity in a special cosmic position reminiscent of ancient geocentric convictions. Yet this central location results not from cosmic design yet from the fundamental physics of observation and light travel duration. Every observer in the universe sits at the center of their own observable sphere. The observable universe is defined as the territory from which illumination has had duration to reach a specific location since cosmic duration commenced. This generates a personal cosmic boundary centered on each observer's position, rendering every location the center of its own visible cosmos. Extraterrestrial astronomers in distant galaxies witness their own unique observable volumes that overlap with ours in some territories while extending into space we can never perceive. From their viewpoint, they occupy the center of the observable universe, while Earth lies near the boundary of their cosmic boundary. This observational influence results from illumination's finite velocity combined with cosmic duration's finite age. Illumination from distant objects demands billions of years to reach any observer, generating a natural boundary beyond which nothing can be perceived. This boundary forms a sphere around each observer because illumination travels at constant velocity in all directions. The separation to our cosmic boundary measures 46.5 billion light-years in every direction due to cosmic expansion throughout light travel duration. Objects that emitted illumination shortly after the Big Bang have been transported to this separation by expanding space while their ancient photons traveled toward Earth. Yet our central position comes with profound limitations. We can witness only a minuscule fraction of total cosmic volume, with most of the universe lying perpetually beyond our perception. Our central location within the observable sphere provides no special access to cosmic secrets or privileged information about universal contents. The observable universe also transforms continuously as illumination from increasingly distant territories reaches Earth for the initial time. Our cosmic boundary expands by 1 light-second every second, gradually exposing nascent cosmic territory. Yet cosmic expansion simultaneously transports other territories beyond our permanent observational reach. This dynamic boundary means that the observable universe represents a moving window through cosmic space and duration. We witness distant galaxies as they existed billions of years previously, while nearby objects appear in relatively recent configurations. Every cosmic observation involves observing backward through duration across varying separations. Our central position also determines what physics we can investigate directly. Physical principles must be inferred from observations within our limited cosmic volume. Territories beyond our boundary might operate under distinct physical constants or alternative principles that we cannot perceive. The cosmic microwave background provides our most distant observable boundary, representing the surface from which ancient illumination initially traveled freely through space. This radiation wall surrounds us at maximum observational separation, marking the boundary of everything we can potentially perceive using electromagnetic radiation. Beyond this wall lies a universe we know exists yet can never witness directly. Our central position within the observable cosmos grants us no special cosmic significance beyond the accident of our particular location. The Hubble volume represents the maximum sphere of space that Earth could theoretically influence through any physical process. This cosmic domain measures approximately 14 billion light-years in radius, encompassing every territory where signals transmitted from Earth could potentially arrive before cosmic expansion transports them permanently beyond reach. Within the Hubble sphere, space expands at exactly illumination's velocity relative to Earth's position. Territories closer than this separation recede slower than light velocity, permitting signals from Earth to eventually overtake the expansion and reach their destinations. Beyond the Hubble separation, space expands more rapidly than illumination, rendering communication impossible regardless of signal strength or transmission method. Validated computations demonstrate that radio signals transmitted from Earth today could theoretically reach any galaxy within the current Hubble volume, though expedition durations would span billions of years for the most distant targets. These signals would arrive severely weakened by cosmic expansion and the inverse square principle governing electromagnetic radiation. Yet the Hubble sphere shrinks continuously as dark energy acceleration increases cosmic expansion rates. Galaxies currently within Earth's sphere of influence cross beyond the Hubble separation at an accelerating pace. Each day, cosmic territories equivalent to millions of Earth-sized volumes pass permanently beyond our ability to influence through any physical mechanism. This shrinking sphere of influence generates a countdown for cosmic communication. Any communications Earth might transmit to distant galaxies must be transmitted before those targets cross beyond the Hubble separation. Once cosmic expansion transports them beyond this boundary, no signal from Earth can ever reach them, regardless of transmission power or duration. The concept of the Hubble volume also applies to receiving signals from distant origins. Galaxies beyond the Hubble separation cannot transmit signals that will ever reach Earth because space expands too rapidly for illumination to overcome cosmic recession velocities. We exist in permanent isolation from most cosmic territories. Current expansion rates suggest that the Hubble sphere harbors roughly 10,000 times fewer galaxies than the observable universe. Most cosmic companions we can perceive today lie beyond our sphere of influence, meaning we can witness them yet never communicate with them through any physical process. Yet the Hubble volume represents more than just a communication boundary. It defines the maximum territory where Earth's gravitational field could theoretically influence distant substance. Beyond the Hubble separation, cosmic expansion overcomes any gravitational attraction between Earth and distant objects. This gravitational isolation means that most substance in the observable universe will never engage with Earth through any physical force. The galaxies we witness beyond the Hubble sphere might as well exist in separate universes because no causal connection can ever form between them and our location. Advanced civilizations within our galaxy could theoretically coordinate to transmit more powerful signals toward distant targets. Yet, even these enhanced transmissions confront the same fundamental barrier imposed by accelerating cosmic expansion. The Hubble volume also determines the maximum territory where Earth's existence could potentially influence cosmic development. Beyond this sphere, the universe develops independently of any actions taken within our cosmic vicinity. Most of the cosmos remains perpetually beyond human influence or engagement. Beyond our cosmic boundary may lie infinite quantities of parallel universes, each harboring distinct versions of reality where alternative chronicles unfold according to quantum possibilities. This multiverse hypothesis emerges naturally from cosmic inflation theory and quantum mechanics, suggesting that our observable universe represents just one bubble within an infinite cosmic formation. Eternal inflation models propose that nascent space constantly forms through quantum fluctuations in the cosmic vacuum. These fluctuations generate bubble universes that expand into separate cosmic domains, each potentially developing distinct physical principles and harboring unique arrangements of substance and energy. If eternal inflation proves accurate, then every possible quantum outcome occurs somewhere within the infinite multiverse formation. Alternative versions of Earth exist where distinct evolutionary trajectories led to variations in chronicles, biology, and human development. Some parallel Earths might shelter dinosaurs that never went extinct. Others might harbor civilizations far more advanced than human society. The mathematics of infinite space suggests even more extreme possibilities. In an infinite multiverse, every possible arrangement of atoms must occur somewhere, including perfect duplicates of our observable universe repeated throughout cosmic space. Identical copies of Earth harboring precise duplicates of every human being would exist in quantities approaching infinity. Yet these parallel worlds remain perpetually inaccessible from our cosmic domain. The expansion rate between distinct inflation bubbles surpasses light velocity by enormous magnitudes, preventing any communication or travel between separate universe territories. Each bubble develops in complete isolation from its parallel companions. Some quantum interpretations propose that parallel universes form every occasion quantum configurations make probabilistic choices. Each possible outcome branches into a separate timeline, generating infinite quantities of parallel realities where every conceivable version of chronicles occurs simultaneously. These quantum parallel worlds might exist in higher dimensional spaces that intersect with our three-dimensional reality only at quantum magnitudes. Advanced physics theories suggest that our familiar space represents a lower dimensional surface embedded within higher dimensional formations called branes. String theory models propose that multiple brane universes could exist within the same higher dimensional space, occasionally colliding to generate what we witness as Big Bang occurrences. Our universe might represent just one brane among innumerable others floating through dimensions we cannot perceive directly. Yet parallel universe theories remain largely speculative because they make predictions that cannot be tested through direct observation. The evidence supporting multiverse models comes primarily from theoretical consistency rather than experimental validation. Recent observations of cosmic microwave background patterns might provide indirect evidence for parallel universes. Some theoretical models predict that collisions between bubble universes would leave detectable imprints in the radiation from our cosmic boundary. Advanced search algorithms analyze cosmic microwave background data for circular patterns that might indicate collision signatures from neighboring universe bubbles. Several candidate signals have been identified, though their interpretation remains controversial among cosmologists. The discovery of parallel universes would fundamentally transform human comprehension of existence and significance. Every possible version of reality would exist somewhere within the infinite multiverse formation. Our observable universe, harboring 2 trillion galaxies and more stars than sand particles on Earth, might represent an infinitely decimally small component of total cosmic reality. Theoretical physics suggests that our complete observable universe, harboring 2 trillion galaxies across 93 billion light-years, might be smaller than a subatomic particle within a vastly larger cosmic formation. This consciousness-shattering possibility emerges from models proposing infinite hierarchies of arrangement extending far beyond anything humans can witness or conceive. String theory and quantum gravity models suggest that spacetime itself may be quantized at the smallest magnitudes, comprising discrete components smaller than anything current physics can measure. If space truly comprises quantum pixels, then our observable universe might harbor only a finite quantity of these fundamental spacetime components. Yet, infinity permits structures of unlimited complexity within any finite volume. Mathematical models propose that infinite amounts of information could be encoded within arbitrarily small territories of spacetime through fractal arrangement or higher dimensional compression methods. These possibilities suggest that our cosmic boundary might represent just one tier in an infinite hierarchy of nested realities. Formations within our observable universe might harbor complete cosmos of their own, while our universe might exist as a component within incomprehensibly larger arrangements. Advanced civilizations within our galaxy might possess technologies capable of accessing information stored at quantum magnitudes. Theoretical proposals suggest that enormous amounts of computational power could be packed into microscopic volumes through quantum processing methods that exploit fundamental properties of spacetime. Yet, the infinite hierarchy concept extends beyond simple scaling relationships. Each tier of arrangement might operate according to distinct physical principles or mathematical foundations. The physics governing our cosmic magnitude might break down completely at larger hierarchical tiers. Some theoretical models propose that consciousness itself might exist at multiple hierarchical magnitudes simultaneously. Human awareness might represent a low-tier phenomenon within vast cosmic intelligences that think thoughts lasting millions of years while processing information across galactic separations. Conversely, the neural activity within human brains might harbor conscious entities existing at shorter duration magnitudes, experiencing complete lifetimes within what we perceive as single thoughts. Each tier of consciousness might remain unaware of the others despite sharing the same physical substrate. The infinite hierarchy hypothesis also applies to mathematical reality itself. our universe might be one fragment within an infinite mathematical library, each entry a unique reality governed by different geometries, dimensions, and laws. Perhaps mathematics doesn't describe reality. Perhaps it creates it. Simple equations like Mandelbrot sets and cellular automata reveal how endless complexity can emerge from basic rules. If the cosmos follows similar logic, what we see may be just the surface of infinite depth, stretching both outward and inward beyond human comprehension. Shrink our entire observable universe to the size of an atom and imagine it existing within a larger cosmos. The scale difference would dwarf even the gap between an atom and our universe. Some theories suggest this is not imagination but reality. Eternal inflation could spawn infinite bubble universes, each a microscopic speck within a greater whole. This hierarchy might continue forever. Our cosmos could be smaller than an atom in a vaster reality, while each atom here might contain universes of its own. Reality could be fractal, complex at every possible scale, infinite in both directions. Modern physics suggests that information, not size, defines importance. Our universe holds around 10 superscript 1 superscript 2 bits of information. That unique pattern could make it significant to higher cosmic intelligences existing on scales beyond our perception. Consciousness itself may exist across magnitudes, vast minds encompassing universes, and microscopic minds living within quantum processes of our brains. Every event, human, stellar, or galactic, might be a tiny vibration within an incomprehensibly larger system. Yet even the smallest structures could hold entire worlds within. Space itself, filled with flickering quantum particles, may be the surface foam of a deeper ocean of existence. You are reading this on a planet orbiting an average star, one among 400 billion in the Milky Way, a galaxy among 2 trillion others. Each galaxy contains billions of stars and countless worlds, some likely older and more advanced than ours. Yet our observable universe might be only a fraction of total reality, with infinite regions beyond our cosmic horizon. Parallel universes may hold alternate versions of history. Infinite hierarchies might nest our entire universe within greater ones. This perspective makes us both insignificant and extraordinary. Tiny patterns of matter capable of contemplating infinity. Humans arose from simple chemistry, yet we've uncovered truths spanning billions of light years. The atoms in our bodies were forged in ancient stars. The universe literally became conscious through us. Despite our smallness, we've glimpsed the vastness of existence. The universe is not only stranger than we imagine, it is stranger than we can imagine. And somehow we are here to witness it.